A on that. So for that, ideally you should know the spectral measure of A, and then you can compute all the probabilities. But we can compute the moments directly. The moments, the nth moment of A on U state U is given by, you take nth power of A, taken upright. Okay. So this is the nth moment. So Mn. So it's actually surprising initially that you take any self-adjoint operator, take the powers and take the diagonal entry, and it automatically is a moment sequence. But it is, and so that means you have to look at powers of A acting on U. So then that's what we did. So we looked at this sequence U, AU, A square U, etc. And we do Gram-Schmidt on this. Okay, so it's simple Gram-Schmidt. And initially we made two assumptions, namely that these are linearly independent and their span closure is the whole space. Okay, that means U is cyclic, right? So if the span closure is the whole space, then we call it cyclic. So there were two assumptions. First assumption was that this is linearly independent. The second assumption was that this same thing, the span closure is the whole space. Okay, that was assumption 2. But then later we said, okay, we can remove them. So with these assumptions, what we showed was that we get an orthonormal basis by the Gram-Schmidt E0, E1, E2, etc. So orthonormal basis of H, and A has the form A0, A1, A2 like this, and E0 like this. This kind of form, tri-diagonal form or a Jacobi form. Assumptions are not there, they are not linearly independent, then it will just truncate after some time. You have to just stop there. Okay? So that happens if means if its A is like if H is finite dimensional, or if means if the measure is concentrated on a finite set, then that happens. And if the span closure is not the full space, then you just break it up, H into the span closure, direct sum its orthogonal complement, only this part matters. So then we connected the whole thing with these coefficients with orthogonal polynomials. Right? We truncate this at the nth place, like this up to n minus 1. So n cross n matrix. Take Pnx as determinant of xi minus an, because P0 of x is 1. P1 at x, if you see, is x minus a. So then, by simply expanding the determinant using the last row, we get recursive relations. Right? So Pnx equals x minus an minus 1, an minus 1x minus bn minus 2 square, n minus 1x. These are so-called three-term recurrence relations for orthogonal polynomials. Okay, and we also see that Pna acting on the starting is not 1. So if you want to normalize it, you can just divide. So take 2nx equal to pnx by cn. So then these are orthonormal. This is what we did. Now, so this is the distribution of A on the state E0, right? E0, which is same as U. Okay. So you may ask, what is the distribution of A if we have this tridiagonal thing on other basis vectors, say on some Ek? What is the distribution of that? Comes out easily from here. Okay. So that is the pure state. What do I have to do? I want to compute, say, the moments, say, so Ek, and then I can actually do any function of A. Ek. So this kind of expectation of a function of A, if I want to compute, okay, I can do it because so this is expectation of any function of A. You can take any polynomials in the pure state Ek, but this is, if you see, this is Pn of A E0 is this. So if I say P1 of A E0 is Cn, right? Because if I divide by Cn, I get that. So this is really 2k of A on E0. So this is f of A. Ek I can write as 2ka on E0. Okay. But these are all real polynomials, so I can take this to the other side and it becomes E0 f of A 2k of A whole square on E0. So this is the expectation of A. Of f times this. So this is the expectation of f times k square on the pure state E0 with our original state E0. Okay. So if you like, I can write it as integral f of x 2k square x mu dx. The original measure was mu. If the original measure was mu of A on E0, then this is the expectation of f times 2k square. So that means f of x 2k square x mu dx. So this is showing that the new measure is absolutely continuous with respect to mu, and the density is with this. So the new measure is 2k square times mu. Yeah. So the new measure, so if I call mu k, so this is k square. So it's absolutely continuous with respect to mu, and with that, okay, with just multiplying with. Okay. Now these things may also explain through another method. Okay. So here, what did I do? I started with the bounded operator and a unit vector, and did the tridiagonalism. Now I can ask this way, can I get any distribution? Okay, because I started with some self-adjoint operator and got some distribution, okay, on the pure state. So can I get any distribution? Okay, so these kind of tridiagonal things, does it describe all distributions? Okay. The answer is yes. So how do you do it? So you now start with a measure mu. So let so this is alternative approach, in the converse direction you can say. So let mu be a probability measure of compact support, say supported on some A to B. The porosity of right. With support contained in some interval. What I mean is the compact support contained in some interval. Like this. So what do? We look at L2 space of mu. So consider, so take the Hilbert space as L2 of mu. Okay. So these are the functions here. Maybe to C mod f square d mu. Right? Actually speaking, the equivalence class of functions. So the L2 space. Okay, so if you start with the probability measure, I can just look at the L2 space of that as my Hilbert space and take so A belonging to P of H defined by A equal to multiplication by X. So that is AF at X equal to X at X, multiplication by X. So that is a self-adjoint operator. Just the polynomials, right? So if your measure is supported on a finite set, then after a finite number of states, they will be linearly dependent and it will end there. Okay. In any case, if it is compactly supported here, the span closure would be the whole space. That was what I was talking about. You need the Stone Weierstrass theorem. Approximation. You approximate all functions using polynomials. So the span closure is whole of H. Whole of H. So that is true. So let us take the general case. So then you would have. So then you get these things, right? The basis you get by orthogonal. You get basis. E0, E1, etc. consisting of what are the basis vectors? They are polynomials, right? You are doing the orthonormal things here, do the Gram-Schmidt here, right? With respect to the inner product coming from this item here. With the Gram-Schmidt, and what you get is an orthonormal basis consisting of polynomials. So they are orthonormal polynomials. So these are nothing but Q0, Q1, Q2, etc. Okay, just a different name, but so En is actually Q1 for every n. Okay, the basis vectors consist of orthonormal polynomials. So all we are saying is that if you look at this multiplication by x, this operator, then look at the orthonormal basis consisting of these orthogonal polynomials, then on that basis A is tridiagonal. Right? The multiplication by x is tridiagonal. And that happens because multiplication by x, take an nth degree polynomial, it can only go up to n plus 1 degree when you multiply it by x. Okay? So it will be this in the span of the things up to n plus 1. But A is self-adjoint, so it forces you to give you the tridiagonal. So you have the tridiagonal relation. Okay? So that is another way of understanding it. So this way you can do, so now instead of compact support, in general case also one can do, it's just that you have to deal with unbounded operators, but we need the moments because we want these things to be in the domain of your operator. So otherwise these vectors are not in the domain and you cannot do anything.
But in the unbounded case, with the moments you get only limited information, right?
Yeah. So the other thing we are assumed is that the span closure is the whole thing, right? So that is in the unbounded case you need the moments, and the second thing you need is that the moments have to determine the distribution. Otherwise you have
as a condition.
Yeah, that you have to put as a condition. Yeah? Otherwise you don't get this as self-adjoint operator. Right? These things means this polynomial means you have to get a core. Right? That won't happen. So you need to put additional things. So I didn't want to get into that technicalities.
Otherwise you'll have too many distributions.
Having the same moments. There are different distributions having the same moments. I can say that you start with this linear combinations of these ENs. Then there are several ways of extending it to get several different self-adjoint operators. Okay, so that would give you several different measures, giving you with same moments. Okay, so they are connected. The moment determining the distribution and whether you are getting a self-adjoint operator or not. And the thing is that this is not new. This was already, if you see the book of Stone, Stone has written a book on linear transformations of the Hilbert space. These concepts are already there. Because they encountered it at that time itself. Okay. There are some things I want to say, additional things here. This explanation, the distribution on Ek is Qn times this. And that follows easily here, you see. The En is Qn. Okay? So So the distribution on En, when you put En, okay, it is the Qn, so you get Qn square. Okay. So these computations which I did here, you can also see directly in that case. Okay. Another curious thing what happens is that if I take so this An, so we have it there. So An is here. So I want to see the distribution of An, right? So instead of going to the full space operator A, I just concentrate on An, fixed N, and see what happens. So then, so eigenvalues of, what are eigenvalues of An?